Question number 1. For a flow in the xy plane, the x component of velocity is given by u is equal to a times x times y minus v, where a is equal to 1 per feet per second, b is equal to 6 feet, and x and y are measured in feet. Find the possible y component for steady incompressible flow. Is it also valid for unsteady incompressible flow? Why? How many y components are possible? Solution. We have u is equal to a times x times y minus b. On putting the values of a and b, we get x times y minus 6. We need to find the value of the y component of the velocity vector v, represented by v vector is equal to u times I cap plus v times j cap. Concepts. As the flow mentioned is steady and incompressible, for steady flow, we refer to it as the condition where the fluid properties at any single point in the system do not change over time. These fluid properties include temperature, pressure, and velocity. The partial derivative of these properties with respect to time is equal to 0. Since the flow is incompressible, in fluid mechanics, or more generally continuum mechanics, incompressible flow or an isochoric flow refers to a flow in which the material density is constant within a fluid parcel. Hence, we can say that the volumetric strain remains unchanged with respect to time. Therefore, the volumetric strain rate is equal to 0, represented by the partial differentiation of u with respect to x plus the partial differentiation of v with respect to y plus partial differentiation of w with respect to z is equal to 0. These partial differentiations or partial derivatives are nothing but the linear strain rates along x, y, and z direction, represented by epsilon x dot, epsilon y dot, and epsilon z dot, respectively. The above equation is also known as the equation of continuity in differential form. For a two-dimensional flow, the equation of continuity can be represented as the partial differentiation of u with respect to x plus partial differentiation of v with respect to y is equal to 0. Or we can write by putting the value of u del x times y minus 6 upon del x plus del v times del v upon del y is equal to 0. On differentiating the term with respect to x, we get y minus 6 plus del v upon del y is equal to 0. On rearranging the above equation in the following order and integrating it as such, we get v is equal to minus y squared by 2 plus 6y plus c. Hence, the possible y component for steady incompressible flow is given by v is equals to minus y squared by 2 plus 6y plus f of x. Here the constant c can be replaced by an arbitrary function f of x. Coming to the next part, yes, the above equation for v is valid for unsteady and incompressible flow. Reason, the equation of v that we have found by the integration of equation 1 previously with respect to the y component of the space coordinate, which is independent of the time variable t. Hence, del v upon del t is equal to 0. That is, the partial differentiation of v with respect to time is equal to 0, irrespective of the condition that it is given as unsteady flow. Coming to the next part, there are infinite solutions possible for the y component. Since f of x is arbitrary, it can take numerous number of solutions or values. The simplest one would be found by setting f of x is equal to 0.